This video is going to explain molar volume of a gas at STP. That's a different section of the map of mole land that will tell you the volume of a gas at conditions called STP. And so it's 1 mole of gas will occupy this volume, and STP stands for standard temperature and pressure. And so if you notice, the way we get between moles and volume of a gas at STP is something called Avogadro's principle. But before we get into that, let's talk a little bit about the difference between solids, liquids, and gases. Solids and liquids have particles that are always in contact with each other. They're held together very firmly in a solid, and they're loosely held together but always in contact because of forces between the particles in a liquid. These two have a set volume, meaning this will never take up more or less space than it does right now. Same thing with this liquid. It will never take up more or less space than it does right now. Gases are different. Gases are moving in 3 dimensions. They can move up, down, side to side, toward you. There are no forces holding these particles to each other. The only thing that keeps them together in one sample is if they are in a container that has walls and they can't escape that. We could make this take up less space if we were able to smash the container down and force all these particles maybe to fit in this space, and if we moved these guys down here, that would take up less space because we would make them closer together. We could also do the opposite, which is we could make the container larger, give them more space to move, and the volume would be larger. That's what makes gases unique, is that they do not have a set volume. However, I'm probably going to say this wrong, Avogadro found out that if you're dealing with a sample of a gas at certain temperature and pressure, they will occupy the same volume. So he looked at these conditions called STP. He said if you study the gases at 0 degrees Celsius and the pressure has to be the same, meaning that they are hitting the sides of their container with the same amount of force, that would be 1 atmosphere, which is basically what you're sitting in right now as the air is hitting you. That's 1 atmosphere of pressure. If you have exactly 1 mole of a gas at those 2 conditions, then it will occupy a size of 22.4 liters. So he came up with, we call it the Avogadro's principle, that if you've got different gases at STP, they are going to occupy equal volumes. We've got 3 different kinds of gases here in this picture. If we have small monatomic gases, those would be things like the small noble gases, helium, neon. They're monatomic. They're very small. The diatomic gases, if we look down here in Brinkelhoff, bromine is a liquid, and iodine, I can cross out just iodine, is a solid. So just nitrogen would be N2, Cl2, H2, O2, and F2. Those are the diatomic gases. And then the large monatomic gases are large noble gases such as xenon, krypton, things like that. It doesn't matter if it's small, diatomic, or large, it's still going to occupy 22.4 liters if you have exactly 1 mole and it's at these conditions of STP. It only works at these 2 conditions. We can take that information and make it into a conversion factor. So it would occupy 22.4 liters if we have 1 mole of gas, or if you have 1 mole of gas at STP, it's going to occupy 22.4 liters. We can use this in dimensional analysis to figure out the size of our sample. So in the example 1 here, we want to know how many moles of gas at STP are needed to fill the Goodyear blimp. The Goodyear blimp has a volume of 5.74 times 10 to the, that looks like a 6 liters. So if we set this up, I didn't leave myself a whole lot of space, and we pick from one of these 2 conversion factors, because they gave us the volume of the blimp in liters, we're going to pick this version that would put the 22.4 liters underneath and 1 mole on top. That means I'm going to take 5.74 times 10 to the 6th and divide it by 22.4 liters. When I do that, I get quite a large number that I'm going to write right here. It's 250, and that's going to be in moles. We go back to the problem and see that that's 3 significant figures, so I keep these 3. This would become 256, 000 moles, which ideally we would write in scientific notation as 2.56 times 10 to the 5th moles of gas. So if you notice on your map of mole land, it's just an extension. It comes off of moles. And so there's one on each side of the mole ratio bridge. That means that we could use this in a stoichiometric calculation. In your packet on the combustion page is where you'll find all the STP calculations. So this is the example reaction at the top of the page. It talks about liquid ethanol, which is C2H5O8. It says it combusts. Sorry, that's an H. And they want you to write and balance the equation. Well, ethanol is C2H5OH. And then since it combusts, that means it burns in the presence of atmospheric oxygen. The products of combustion reactions are always carbon dioxide and water. And then we have to balance this equation because we can see that we don't go in with the same amount of carbons that we come out with. So to balance this equation, the coefficients I need to put in, if I make this a 2 to balance the carbons, and I make this a 3 to balance the hydrogens, then I just have to come back, make this a 3, and we balance the oxygens on both sides. Now I have a balanced combustion reaction, and I can do this stoichiometric problem down here. They want to know how many liters of oxygen gas are consumed if 2.5 moles of ethanol combust, and they've used the key phrase here at STP. Saying STP allows me to go up here and use the 22.4 conversion factor. So if I write the setup for this problem, X liters of oxygen gas are equal to 2.5 moles. We have an abbreviation for ethanol. It comes from the biology world. It's ETOH, and I'm going to use that because it's really much faster, of ETOH. So if I have 2.5 moles of ethanol, and I want to know how many liters of oxygen gas that is, I'm going to go to the map, and I'm going to say they've given me 2.5 moles of this chemical that I'm starting with, and they want liters of not this chemical, but the other chemical. I'm trying to get right here. That means the first conversion factor I'm going to need to get towards my destination is the mole ratio from the balanced equation. So I go up to the balanced equation, find the ethanol. This is ethanol right here, and then I find oxygen. So here are my ethanol and oxygen. These are what I'm going to make my mole ratio from. I don't really care about any of this because the problem didn't mention that. So the ethanol would go on the bottom so that the moles of ethanol will cancel. There's no coefficient there, which is an implied 1 mole of ethanol. And then there is a coefficient here of a 3, so that's 3 moles of oxygen gas. Okay, so I've done my mole ratio. I see that moles of ethanol and moles of ethanol cancel, and I've now crossed the bridge, and I now have moles of that chemical, a different chemical than I started with. And now I'm ready to go up to the balloons, use Avogadro's principle, and get to the moles of gas at 22.4 liters per mole. So the way I'm going to set it up is so that the moles are underneath. So it's the molar volume. 1 mole of oxygen at STP would occupy a volume of 22.4 liters. That means I can cancel the moles of oxygen. I'm left with liters, and that's what I wanted was liters. And because this was oxygen, then this is also going to be oxygen. All of the numbers are on the top. There's only ones underneath, which means I'm going to multiply these 3 together. So I multiply 2.5 times 3 times 22.4, and the calculator gives me 168. That's going to be liters of oxygen. The problem only gave me 2 significant figures to work with, so I'm going to keep these. This is going to be garbage. It's greater than 5, which means I'm going to bump that up. It's going to become 170 liters of oxygen.